Okay, so you've heard a great talk just before about how to use neural networks to translate. And this has been quite a big thing in all of natural language processing. So people have been doing a lot of stuff in natural language processing, parsing, translation, finding entities, anything towards making machines understand text a little bit. And then came these neural networks, and as you've seen in the previous talk, the main thing is they generate the next word, right? They look at the past, maybe have some recurrent neural networks, maybe some other mechanism. And the thing they're trained on is to generate the next word of the output. And mostly, for the last year and a half or 2 years, which is like distant past in deep learning, prehistorically, it's been done with RNNs. So you have this LSTM cell. It generates the next word, and when I started looking at it, I like didn't believe that you can train something that will translate from English to German from raw data with such a generic model. I mean, you've seen the previous talk, and all the kinds of mistakes it does, and the phrase-based and non-phrase-based systems, but to me, I'm not sure if you got this vibe that this is something incredibly amazing, because it's a generic system. It's 4 lines of equations, and you give it data, and it learns to translate. It learns to speak fluent French, and actually on context from English, right? But this has been done. So what's missing? Well, the translations you saw, they have some problems, some mistakes, and we were thinking for a long time, like what's the gist of this problem? What is not so great about it? And it turns out these neural networks, you translate sentence by sentence. You do it like on the level of tokens or words. So a sentence maybe has 40 words, a long one maybe has 60. But when we speak, we think about context that goes way beyond that, right? When I speak, when I go to see my old friend, I will start talking to him about things we talked about 20 years ago, maybe, and I'll know it. I'll immediately recall what's needed there. And this thing, which people call different names, maybe long-range dependencies or long hop gradients, it seems to be like one really important thing to solve and to tackle to make these networks like understand more. And so if we train the network with a long range, with something that can really look back many thousands of steps and remember it, well, we could train a translation, but translation is usually sentence to sentence. And I'll tell you the details about this model in a moment. But imagine if we just trained it to generate text, to write something. And since we want it to be longer range, let's say we train it on Wikipedia articles. Okay? So that's called a language model, something that just generates the next word. Since it's a model, it's probabilistic. So it's a probability distribution over various articles. But we trained one, and this is what it generates. So the only thing it's conditioned on is the title, which is the transformer, because that's the name of our model. So let's see, the Transformer are a Japanese hardcore punk band. And it's trained on markup, so it generates markup too. And then it goes on. In the early years, the band was formed in '68 during the height of Japanese music history. Among the legendary Japanese composers of Japanese lyrics, they prominently exemplified Mohoro Oda's especially tasty lyrics and psychedelic intention. I don't know what the creative part here thinks of this. But it starts as a Japanese band. Then it goes on. And, it generates history born from the heavy metal revolution. In 1977, well, there kinds of goes off in the things. Let's go on. They generally played around Japan, growing from the top 40 standard, and then in '81, the bassist Michio Kono and the members of the original lineup emerged. Right? The interesting part is it makes up some names, and then we went to Wikipedia and checked. These people don't exist. Neither does this band or anything like this. It's all totally made up. And but it makes up this bassist, and then he is the original founder, and then there is Niji Fukuna, and you can see that since it decided it's a Japanese band, it has kind of Japanese sounding names, and it knows that the band should have a history and so on. And it goes on, and then there is the band to split, right? Then in 2006, the band split up, and the remaining members reformed under the name Star Mirror, with Kono in tears. So this is totally made up by a language model. And, well, but this is not a hand-picked example. It's just sampled from a distribution. You sample again, and you have another thing. The Transformer is a book by British Illuminatist Herman Weirhead, set in a post-apocalyptic world that border on a mysterious alien known as the Transformer planet. Well, it should have a different name. And you see, it knows the book has a summary, and then the book covers the world of binoculars from around the Earth, and so on, and conceptual, the Transformer universe. Principles, a setting man named the Super Congo planet, who's a naturalistic device. I don't know, sometimes it gets too strange. But what's interesting, it makes a quote from the book. It actually learned that inside Wikipedia pages about books, you have quotes from the book, so it makes a quote, and a man called Dick Lantani Bartow, known as the greatest radio, whatever. It's a strange thing. So this was a model that was trained only for like 2 days on 8 GPUs. We have better models now, and it's very interesting. The better models, they like learn to make up poems in the middle of articles about lyrics, and they keep consistency. If it's a Japanese band, it keeps talking with Japanese names about Japan. It refers to the members. It refers to the years that were there before. So, I mean, I want to give you the feeling that this is something exciting. This is not something computers were able to do like a few years ago. Yes?
The coherence of the article is because the data is homogeneous, or because he somehow remembers what he has.
It remembers what it generated before.
So it's
yes.
not because the data is.
Well, the data are full Wikipedia articles, so they are coherent, and it learns from that. It learns that.
But for example, all the Japanese band articles, old articles. So
it isn't a selected data set of just metal.
No, it's trained on all English Wikipedia, okay. All of English Wikipedia, and so. How does it work? So you heard about RNNs, but RNNs have this problem that if you try to generate 2,000 words, the state and the gating in the LSTM would start to make the gradient vanish. I mean, it's called long short-term memory, but it's not that long. So people started to try to solve this with convolutions. That was like last year. When you take a long sequence and you make convolutions and convolutions, you can get I think that's easier to see on the picture. So if you make an RNN, it needs to go like one word at a time. So to get to here, you need to see maybe the 1,000 words before, right? Then came this model from DeepMind called WaveNet, and then for translation it was called ByteNet, but it's all the same thing, which is we make a convolution on the lower layer to jump two steps. And then the next layer skips one at every point. So it skips one here and skips one there. So in the second layers, you see 4, right? The next layer skips 2 or 3, so you see 8. So for a logarithmic path, you'll get to this word with logarithmic number of layers gets to see a context. So it's much better. It's not linear like with an RNN. It's logarithmic. And they had some success translating with this. It was not bad. But it still has, like, it's very positional. Every layer looks like this guy sees the word number 13 before me. Why is word number 13 before me important? Maybe in this sentence it's number 12. It seems like this scheme is referencing things very much by position, while referencing by content would be a much more natural thing. So how do you reference by content? Well, there is this mechanism called attention that was introduced already with LSTMs, but just look at one thing. And attention is something where you make a query with a vector, and then you basically look at similar things in your past. So while convolutions are quite a positional thing, that's where you have a different color for every position, attention looks at everything, but gets things that are similar. So maybe this guy is very similar to what I'm looking for, and this one is not at all. That's the general idea. So when you retrieve similar things, you can look at a very long context. And so imagine you're producing the name of the band member, right? Now you can attend however many steps behind. You can see, oh, earlier I said it was Michio Kono. Let me say this again, right? And with CNNs, you could do this, but you'd need to know the exact position. You'd need to compress the data very much. With attention, since it's content-based querying, you can do this quickly. So, okay, so there are attentions. What I showed you is a language model, meaning it just decodes. It has no inputs. But for translation, you need an input. So you need an attention that's from the output attends to the input. You need an attention in the input, which can attend everywhere, and an attention in the output, which only attends to things before. Now, can anyone tell me what time it is?
It's
Okay. So I have, when am I supposed to stop? So
you can go.
I can go. Okay. So let's look at the details of the model. We have some inputs. It's, say, the English sentence, right? And then there'll be a multi-head attention. I'll go into detail of what that is later. Then there'll be a feed-forward layer. Just every word will be processed. And that's the processing of the input. Now, when we start generating output, we need this masked attention, which is like the one here. Now, I'm not sure if this is doing justice to that idea. So in a recurrent neural network, it's very clear that you go from one word to the next, right? If you, in the more standard attention things that have been there for a while, you attend to everything there and back. But if you wanted to make a language model, you cannot do this, because at the end, you're predicting the output. So from this word, you're predicting the next, meaning this word. If it could just attend to it, it will look at it and copy, but there will be no way to decode. So this would be a model that, well, it would train immediately, but had no way of inference. You could never generate anything. The trick is you want to attend to only things before you. So how would you do this? In an RNN, you can do it, but it takes you every step, every word that comes in, you process it in one step. Meaning if you have 2,000 words, you need to make 2,000 consecutive steps, which is a lot. And it takes a lot of time. It will take you months to train, and you'll not be too happy. Now, in our model, which is gone, in our model, you have the outputs, they come in, and then there is the masked attention, which is a single matrix multiply with a mask. So all of these things, they're done in parallel. You have 1,000 words, they come as one tensor, that's 1,000 by something long, and then every word I needs to attend to all words before it, which will be done by multiplying everyone with everyone and masking out half of this with zeros. So this step, which does attention for maybe 2,000 words with 2,000 words, everyone to everyone, is a single matrix multiply. And the GPU hardware is extremely optimized for large matrix multiplies. So this can happen in a very quick time. And then you do this again, but then multiply with this. OK, have a feed forward, and then do a prediction. In the sense of neural network architecture, this is a very simple few-layer feed-forward architecture. In a way, it's much simpler than the RNN. It has no recurrence. There is no weight sharing. Everything happens in a bunch of masked matrix multiplies. So what is exactly this attention? So we define attention. There is a query that will be a vector. And then there is this key and value matrix, which is your memory. So you can think like this is the current word, what I'm operating on. And this is all the past, all the words I've generated before. And keys and values can be the same thing, but they don't have to. That's why we write it like this. So what you want to do in attention is take the query, find the most similar key. As I told you, it's a similarity thing. And then get the values that correspond to these similar keys. But of course, it's soft. It all needs to be differentiable. So how to do this efficiently? Well, you take the query, multiply it by the transposed keys. So that's a matrix multiply. Then you take a softmax, which is like this exponentiation and normalization. And that gives you a mask. That gives you a probability distribution over keys, which is peaked at the ones that are similar to the query. And then this mask, you make a matrix multiply with the values, which is the same as summing over values multiplied by this mask. And there you are. You've retrieved what you want. You've done 2 matrix multiply and 1 softmax operation, which is very fast. Actually, you need to normalize it a little bit to train well, but that's a technical detail. And that's it. So how costly is it actually? Well, if you have a recurrent neural network, let's look at that first. You need to make n steps. Every word needs to make a step. And in every step, you have this dimension by dimension operation, maybe a bunch of them, but generally it's d squared when d is your hidden dimension of the network. Attention is a little scary because it has this n squared thing. Everyone is attending to everyone before it. So that's very scary, and it's scared me for a while. I was telling maybe we shouldn't get into it. It's n squared, and then, if you do any theory, you'd say, oh, that must be worse than this. But then, luckily at Google, there is this guy Noam, and he never got his bachelor, but he wrote most of these papers. And he says, well, D is usually at least 1,000 in our large networks, while N is the number of words in a sentence, so that's like 70. So what are you talking about? This is 70 times 1,000 squared. This is 70 squared times 1,000. You're totally wrong. In most cases, this is smaller. And when we get to more than 2,000 words, we can find out ways to do more smarter things. But let's first do that. So we did it, and so one problem with attention, since it's just a similarity measure, it works as if this was just a set of words. It has no idea that this word comes after this, because it just retrieves the most similar ones. But it's really important. The order of words is not arbitrary. You cannot just reorder and hope that it will translate well or generate the right next word. So you need to add some timing signal, and you need to add a little bit of the positional things. So we have a multi-head attention with positional signals. I will not go into the details of how this is done. So there'll be multiple attention heads looking at different words, and they know the positions. Okay? So we'll have better pictures in a moment. Right, so we built this model. It has multiple layers of these attentions. And as is standard now, we trained it on translation. And then, deep learning is a trade, right? You need to do all the tricks to make things work actually well. So you need to have dropouts in the right places. You need to use the Adam optimizer and maybe think a little bit about your learning rates and how to decay them. We use something called label smoothing in the softmax, and then when you start actually decoding from this model, you need to pay some attention to what you're doing. So there is a bunch of technical items that we did, and then that was, I think, the 5th time I did them. And then we also started thinking, well, it's actually quite tricky to do them all right. And since this was my 5th time, and also I did it with other people, I realized that the previous 4 times I always had some bugs. And then we thought, okay, so if someone from outside of Google Brain, where you luckily have, like 20 people who've been doing this for longer than almost anyone else, and they can tell you what you're doing wrong, it's very hard to do this right on your own. So we decided to make a library where you could at least look at the code and get these things right. And I'll talk a little bit later about how this library came out. But then, then we started doing this machine translation thing. And I don't know if you got this blue from the previous talk. So there were like these phrase-based systems, and on this quite standard English-German things, they got like 20.6 blue or something like this. And then came the so this was the Google production paper, it got 24. Then there was a very recent Facebook paper that used convolutional things, it was 25. There was a mixture of experts layer paper, which is this model with some extensions, it got 26. So this was considered very high. If you give this to human translators, they will get something around 30. So this is kind of pushing, and of course, blue is a bad metric. Like, you can get 30 with something that still makes totally stupid mistakes, and these networks are by no means perfect. But in terms of this metric, this seemed quite high. So people said, yeah, you're doing another architecture for translation. What can you get? You'll get 26.5, should be very happy. So we were, and then there were ensembles, and you see they get like 26.4. And then we were extremely happy because we trained this big transformer model, and it got like 28.4. And that's a very high number. And we looked at these sentences, and they were really better. Like, they're reordered in a better way. The words come in a better position, and we tested what parts of the architecture matter most. But here is a funny thing. So who knows about the Winograd schema? So Winograd was the scientist, and he was thinking, what's a good challenge for AI that would have to do with language? And then he thought, well, there are these things where you really need to understand the meaning of the words. Let's say I tell you, he didn't put a trophy into the suitcase because it was too small. What was too small? Right? The suitcase. And if I say because it was too big, it was the trophy. Now, okay, this is obvious to everyone. No human will ever make a mistake. When you translate it into French, and also into German, trophy and suitcase have a different gender. There is simply no way you can translate these two sentences correctly without having quite a deep understanding of what's happening in the world. And it's totally not clear how a neural network would be able to get an understanding like this. And indeed, if you try a few Winograd schema sentences, there were no machine translation models that did any good on them. Not Google Translate, not the LSTM models, not phrase-based translation by any means. So we threw them at our new model, not expecting too much. And then it started doing some interesting things. It doesn't get them all, but this is a shorter version. The animal didn't cross the street because it was too tired or because it was too wide. You see the same pattern. And then because there are these attention heads, so when it's producing the word it, we can check where, so there are like 40 of these attention heads. The blue one is just one. And it looks at the animal and street. So this is the attention mask, the query multiplied by key. And the stronger color means that it's the bigger strength. So you can see that it looks at animal and street, and here it focuses on animal more. While here, it also looks at them both and focuses on street more. Now, it will not get everything right, but what this shows you is that this model has the capacity of thinking about relations, because it can retrieve these two things, and in the next layer start processing this to decide what to output next. So here is a bunch of this Winograd schema sentences, and Google Translate gets one or the other wrong, while we get, like, these two we get correct, these two, this we get wrong. Well, I think it's a very interesting thing with these attention heads, that some of them you can actually interpret. You can see, like, this head, it always looks, when it produces pronouns, it looks at things that it basically does coreference resolution. It looks at what should it stand for. There is always another head that whatever word it is in, it looks at the head noun of the sentence or the head verb. It just wants to know what are we talking about here. And it's really funny. The bigger you make the model, the more data you have, the more interesting things you start seeing with these attention heads. And okay, so that's the transformer model. And then another project was to think, okay, so it does very well on translation. It produces nice language. Can we do multitasking with this? Could we do a lot of things in common? Because it's fun to generate language, but it would be even better. Well, we need to train one model for translation, one model for parsing, one model for entity resolution, one model for grammar correction. It becomes boring at some point. It's like, couldn't we just train one model? So we started thinking in this way, and then we thought, okay, if it's one model, then it also should do images and speech. But then, how do you put an image together with a text? Well, the image is a 299 by 299 pixels, and the text has these tokens and stuff. So we didn't, like, it didn't seem like you can just put them together in one place. So we made these small things, which we call modalities, that take the raw input and process it a bit and return a compressed representation that's of a similar size for all different modalities. And then we trained it on 8 different tasks. So we trained it on 4 translation tasks, the ImageNet, image classification task, image captioning task, and what else? Oh, parsing and speech recognition. We thought, okay, let's give it a go. And then it failed totally. I mean, it either did one of the tasks and not the other, or it didn't do any of them. So we started working on it, and one thing that, I mean, there were a bunch of things that were important, but there is this thing called mixture of experts. And it's a technique that allows you to make your model big without making it slow. So normally when you make your model big, you increase this D we have, the hidden dimensionality. But then every matrix, every weight matrix is D squared. So every time you run the model, no matter what, you do these D squared multiplies, and if D is 10,000, it's 10,000 times 10,000, it cannot be fast. Now, mixture of experts is you have, say, 100 matrices, or maybe 1,000. And you will have a gate that your model will learn, and it will only pick 4 of them. It will multiply by these 4 and ignore the rest and gather the result. but for a different word, or for a different image, or for a different input, it will multiply by another 4. So you get the capacity, you get the parameters. Like in the previous talk, you heard there is this memorization versus deep neural networks. And in some sense, these mixture of experts model allow you to have a lot of capacity to memorize because they have a lot of parameters without paying the cost for speed. So when you train the multimodal, then you have a single model trained on a single run, and well, you need to tell it like what to output, whether it's English or a category or French or German or a parse tree. And then it starts to work. You give it an image and you say, okay, please caption it to me. And this is some man sitting in front of a suitcase. Okay, maybe it's not perfect, but it's something. It can find categories. It can translate from English to French and to German. And it can like give you a parse tree for a sentence. And there are some interesting things that happen without any training. Because you're training a model to translate from English to German and from German to English, from English to French and from French to English. Right? This is the training data you have. But then the model, if you give it French and say to German, it will output you a very reasonable translation, even though it's never seen French and German in its training data. But it has seen English and it manages to connect it. So I think this multitask thing is very fun because it especially improves that on tasks where you have little data. All deep learning is also great, but please come to me with 10 million sentences, right? And getting 10 million human translated sentences is not that easy. Okay, and then I also talked about the library. So since we've been redoing this again and again, we decided to finally make it into a framework and a system, and we call it the tensor to tensor library. It's of course on top of TensorFlow, and it has all the tricks that I was talking about. The optimizer, the label smoothings, the learning rate decay schemes. It's they're well tuned so that you can change the model and play with it and not change the rest of the things. Because of course every training model you download from anywhere will have some label, some say learning rate decay. But you tweak the model and you might need to tweak the learning rate. For example, if you make the learning rate dependent on if your initialization is dependent on the depth of your network, you change the network a bit, you need to change the initializers. Everything is connected with everything, and then you get the model, it runs. You change one thing, it breaks. So we try to avoid that. We try to work with something that's always rescaled to some unit norm and allows you to tweak and build and mix and match without preventing it to work. And we've had a bunch of papers and re-implemented some older models. And so we try to make it reasonably easy to use and install. And of course, it has bugs as every software. But if you're interested, give it a try. And you can run it on translation. And so the earlier translation models. So for example, this one, that's the model that's in the Google Translate currently. It takes it has a fair cost of training. Like 10 to the 20 is not that little. While this model gets a better result with a cost that's like 2 orders of magnitude lower. And 100 times faster is a lot. Like this takes a month on many GPUs and so on. While this you can train at home overnight. And that's fun because you can tweak something and see that it works or make it generate Italian. And you can train a smaller version in about an hour or so. It will not get you the blue scores you want, but it will translate English to German. For me, since we want to try new architectures, we want to experiment with new things and try more distant ideas. I find it fun to be able to train for 1 hour and see, and you very quickly see that no, it's totally garbage. It doesn't work at all. But you know that something can be done with this time. So yeah, I mean, you're welcome to try it out. Add a data set, add a problem, and thank you for your attention. Yes.
This kind of model, obviously in translation, language translation, that's where for one language pair at a time and one data set at a time. Or you can generalize for all language pairs and...
It works as with the multimodal. If it's just language to language, you don't even need modalities, it's the same.
Yeah.
You just need to make sure the vocabulary is the same.
So but you have to train every time a new language pair, the model for new language pair?
No, we train together.
Okay.
We train on four language pair: English, German, German, English, English, French, French, English. It's one training run and one model.
Okay, that's explain the difference in blue score.
No, not for this experiment.
Okay.
No. But we can do this, and it also gets very good results. They'll probably be slightly worse on every single language pair. So to compare things academically, right, to present results, you need to have the same data set as was used before. And all the previous papers are not multilingual. That's why we don't put numbers for multilingual. But you can do this, and actually the production version of Google Translate that you use on your phone, it does have multilingual models because it's just easier to launch them in production. There are 103 language pairs that Google supports. That's a lot of things. If you group them...
The GNMT, all the pairs on GNMT are trained on the multimodal. No.
Yeah, they're grouped into like groups of, say, 8 languages or maybe sometimes 6 or sometimes 10, depends on. And especially if there are languages like the multiple Hindi languages. We have a little, not too much data for them, but they can benefit from transfer learning from others. You group them together, train one model, and of course you need to check whether it gives good results. But yes, the multilingual training, you can do this with many models. You can do this with this model, you can do this with the GNMT model, but it's in general quite a good idea. Although, like for example, French and German, I think the French will be a little bit worse because the French data is one of the largest data sets in translation. Even the public data set is 40 million sentences. So if you're adding German, you're not improving it. The part of the model will be...
Also a problem of morphology, different morphology between languages. The model could be influenced, could be affected by different morphology.
Right. We tried to examine this, and so the hope was that we could see that the languages that are similar in language groups will give bigger improvements. There is not a clear correlation. Sometimes there are strange things happening, like Vietnamese improve Czech for some reason. I don't know. Yes. So
that's perfect for zero-shot translations anyway.
Yes, the zero shot is good because in general we have only X to English and English to X data, but people sometimes want to translate between.
Okay,
yes.
thank you.
Does the net need to be larger if you plan to have a multi-language engine compared to a single language pair engine? Does the net need to be larger, more complex?
Yes, it needs more parameters. You need a larger network. And one good way of making larger is to use the mixture of experts.
Okay.
Because if you make it larger in a naive way, it will be slower. And
Can you tell more about the transformation that you made for project images and text in the same space? Because I see that you use a mixture model. It's not totally clear to me if you made some transformation of data.
yes, so when the image comes, it first has this image-specific part, which is downstrided convolutions. and they make it down into something small like 7 by 7. And then that gets into, and the text, if it's word level, it just gets embedded. If it's character level, it also gets a little bit compressed. And then the small parts, they go into the common joint model. That's stuff.
So there is a discretization which is applied on the image.
There is a
discretization to make it discrete, otherwise the image is continuous, doesn't have really...
I think it's just transformation using convolution now. Is that?
right. So when the text comes in, you embed the words. When the image comes in, you use the pixel as value, as a number, right? You divide by 255, and then you have 3 channels, and then make a convolution from 3 channels to 32 channels.
Okay, no other smart parts in like edge detection to get objects.
No. It's yes.
Okay. I really like the comparison with WaveNet.
Mm-hmm.
WaveNet started generating audio. So I was wondering whether you have any plan to use this sort of transformer for, for example, generating raw waveforms in audio. Replacing, for example, something like WaveNet, which has position very fixed ways of propagating.
Yes, we're experimenting with a bunch of things. It's there are a lot of things, and there are few of us. So so it's we're thinking about it, but it's also open sourced for a reason, right? It's
do you think that in the future we will have even the training open source?
The training is open source.
In this case,
yes.
The training is open source.
Yes,
It's
yes.
not just the library.
No, the library is for. Oh, you mean training?
I mean the training. All the elaboration that you do with the data.
Yes. So the library does everything. It will download the data for you, tokenize it, pre-process it, train the model, and give you something where you can type in text and decode a sentence. Yes, it's end to end. And as long as the data set is public, which not all are, but for translation they are, it will download it for you. Of course, we cannot, like for speech, it's harder because a lot of speech data sets, they require you to register, have a password somewhere, download it, pay some money. We cannot, like...
Okay.
Did you try document level translation?
We didn't, but we should. It's what we did try was, so one problem with document level or context level translation is that its effect on BLEU score is very minimal. We gave to human translators some paragraph level documents and scrambled sentences and then gathered it together, and the difference in BLEU was negligible. And it's very hard to, when you make a system like this, it's not like you train the model and it's wonderful. You spend weeks after weeks on tuning parameters and trying to improve, and to guide this process you need a metric where you're reasonably sure that if you improve it, you've made progress. In the context level translation, it's very hard to work with BLEU. And we don't have a metric to
there is an evaluation run by my former student and other people, so it's about really pronoun, translating pronoun from one language, and it's, I think, a subtask of WMT. So they have data on that, and also evaluation metrics, I guess. Special test cases for which you can check this even Winograd scheme that you told about.
right, but
I think they use context even from other.
yes, I think the
So
translation should happen in context. It's just we need an automated metric, right?
But there is an evaluation framework that's suited for this problem.
So I think it will come.
Sorry, how does this kind of models handle positioning problem?
Oh, right. So yes, I skipped over it. A translation is a bag of an attention over anything is like it was a bag of words, right? It doesn't have anything. So you need to add something. And we tried a number of things. So one thing we tried is for every position to have a separate vector. And it's learned, and this is word number 65. And this works a bit, but it doesn't generalize. So if you have a sentence longer than anything in your training set, it gets confused. So what we ended up doing is to add sine and cosine curves. So for every position I, you will make a position vector, and it will have sine of I, but also sine of I divided by 2, I divided by 4, I divided by 8. So since the vector is of depth d, it can have a lot of numbers. And cosine, for some reason. And so this vector allows you to see on different frequencies. Because what the network really wants is to attend, like at least one of the attention heads will always attend to the word before me. Because it's important to know what just came before me, right? Or two words before me. So this positioning vector allows this, because a lot of these positions, basically all except for one, are very similar to the word just before me. So it can latch on that and attend one before. But it can also attend like 20 before. Seems to be a reasonable way to handle positioning.
Is this model, the attentional model, helpful even outside translation, like voice recognition or emotional analysis? Did you try this approach in other fields?
So there are a lot of problems in language, right, and even besides language. And we are, well, I listed the people, but they also do other things than this. So we're really maybe 3 or 4 people doing this. That's why it's open source, and that's why you're all here. You should go and try. But we tried on a number of tasks. We tried on parsing, and the results were exceptional. So even with the standard parsing data set is 40,000 sentences, which for a neural network is extremely tiny. And for example, an LSTM, a pure RNN model, cannot learn parsing from this. A model with some attention and tweaks gets like 89, and this model gets 92, which is better than the Berkeley parser. And the thing you need to understand, Berkeley parser, like Slav Petrov spent his PhD, and he's a very smart guy, and he spent years writing it. And that's on top of other people who spent decades like writing grammars, probabilistic grammars, latent inference model for them, and they get to 91.5. This thing, which is super easy, and basically all the equations were on the slide, you just run this on this 40,000 data and you get 92. It's in a way depressing, you know, because it means stupidity is enough now. No, maybe not, but yes. So we tried it on a few things. We also tried it on summarization internally. It worked better than any other model. So it seems like if you tweak it, it works really good. We tried it on images, it didn't work so well. So this, but it sometimes is that you just need some other trick.
Thank you.
Okay. Oh.